Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle: electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries, dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the Ice Cube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed two more galaxies, NGC 4151 and NGC 3079, as potential sources of high-energy neutrinos. The findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper Kamiokande and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. DUNE, on the other hand, relies on innovative technologies, that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP violation, could be the key to solving this cosmic mystery, and Hyper-K and Dune are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper-Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over Dune, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the Standard Model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery, the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. The T2K results have only reached about 3 sigma, and this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and Dune in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts, with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which may be even smaller. This realization has sparked a global effort to develop alternative methods and experiments that could surpass the capabilities of CATRIN. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. As we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from Dune, nestled deep in an old South Dakota gold mine, the next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time. Beyond the reach of traditional microscopes and within theoretical physics lies a frontier not so much of remoteness as of possibility and understanding. This frontier is challenged not by physical barriers or vast distances, but by the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the building blocks of technology and reality behave quite differently from anything we have encountered in our macroscopic world. Quantum mechanics is a phrase that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in several places at once. They can spin in opposite directions at the same time. They can be entangled in the vastness of space, acting in concert with no apparent connection. These bizarre behaviors are at the heart of a technology that could revolutionize our world. Quantum computing. In the heart of this technological storm lies a concept so revolutionary and yet so elusive that it challenges our very perception of information and reality. By traveling the quantum frontier, we enter a space where information is not just processed, but exists in states that defy classical logic. Here, quantum bits, or qubits, can store many possibilities at once, compared to the simple bits of today's digital devices. But how to preserve information in a system that loses its essence at the slightest interaction with the environment? And scientists may have some answers to that question, because quantum mechanics does more than just redefine computing. It encourages us to rethink the cosmos, intertwining with the fabric of space and time in enigmatic phenomena such as black holes. These cosmic anomalies are not mere objects, but the key to understanding the quantum puzzles that hold the secrets of the universe's information storage and retrieval systems. Join us on our expedition, an expedition to the frontier of quantum mechanics exploration that may ultimately redefine the meaning of computing, data protection, curing disease, and perhaps understanding the very fabric of reality itself. So you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, where data is processed as a straight series of zeros and ones. In contrast, quantum computing works with qubits, which can embody zeros, ones, or both at the same time, utilizing special properties of quantum mechanics to perform complex computations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in developing quantum computers is creating and maintaining quantum memory. You see, unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause quantum information, known as quantum states, to decohere, that is, erase the stored data. This is like trying to hold a spinning coin on its edge. This susceptibility stems from the fundamental nature of quantum memory. It's not simply a matter of storing data, but of preserving complex quantum states, which are the basis of the potential of quantum computing. Herein lies the paradox at the heart of quantum computing, the no-cloning theorem. This theorem is a unique rule of the quantum world and states that it's impossible to create an exact copy of an unknown quantum state. In the everyday world, if you want to prevent data loss, you can make copies of it. But in quantum computing, it's impossible to make an exact copy of a qubit containing unknown information. This rule is a serious obstacle because it means that traditional methods of data protection and error correction, such as backups, simply don't work in the quantum domain. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They're using quantum error correction techniques that involve entangling qubits, linking them together in complex ways, and allowing the system to detect and correct its own errors without having to directly measure the quantum state. These methods don't just preserve information, they preserve the very essence of quantum behavior. But how can the very gravity wells where not even light can penetrate and quantum computing be related, you might ask? The intriguing connection between black holes and the burgeoning field of quantum computer science begins with one deep mystery they share in common. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed groundbreaking ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma. What happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to quantum computing's problems with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So how much information can a black hole store? Bekenstein in turn presented the concept that the entropy of a black hole, in fact its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. But how can a surface store information, you may ask? After all, you need some kind of structure. You need atoms or something else that can store bits of information. Well, it turns out that you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck units are the smallest measurable scales in the cosmos. These units, named after Max Planck, mark the limits beyond which classical theories of gravity and space begin to break down and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the most minuscule dimensions imaginable. So why is the information content of a region of space equal to the surface area surrounding that region and not its volume? Consider this analogy to better understand the unconventional way information is stored in a black hole. Imagine that your room is not just a library, but a magical library where your entire collection of books can be encoded simply on the wallpaper that covers the walls. Here, instead of measuring the volume of the room to determine how much it can hold, we look at the surface area of the walls. This radical idea reflects how black holes store information, but not in their vast void, but on their outer surface, at the event horizon. And this leads us to the holographic principle, which may seem like science fiction, but it is a serious scientific theory inspired by the thermodynamics of black holes. A hologram, colloquially speaking, is a flat surface that contains all the data needed to display a three-dimensional image. If you apply this to the universe, a startling possibility arises. Everything you see around you, from your cup of coffee to the stars in the sky, could be a projection of information encoded on a distant two-dimensional surface. The Won-Maldacena model, known as the Anti-de Sitter Conformal Field Theory Correspondence, or ADS-CFT, goes further. It proposes that the type of universe described by Einstein's theory of gravity, negatively curved and seemingly limitless, could be equivalent to a gravity-free quantum field theory defined at the boundary of that space. Essentially, it's as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring in it. This revolutionary idea suggests that our understanding of space and time, however intuitive it may seem, may be an emergent phenomena from a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic data storage observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing computations impossible for classical computers. As we move closer to mastering quantum computing, its impact on our future is becoming increasingly clear and promising. This technology doesn't just increase the speed of data processing, it expands our ability to solve problems previously thought unsolvable. Cryptography, medicine, and space exploration are just the beginning. In the field of cryptography, quantum computing is a double-edged sword. On the one hand, they pose a significant threat to existing encryption methods. Traditional security protocols rely on the complexity of factorizing large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods can become obsolete over time, leaving data vulnerable, from your personal correspondence to access to your bank account. However, this same ability opens up the potential for quantum cryptography, which can provide a level of security that's fundamentally unbreakable. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to eavesdrop on quantum keys changes their state, thereby revealing the presence of an attacker. This method could revolutionize the transmission of sensitive information, making our data secure against even the most sophisticated attacks. In medicine, the impact of quantum computing could be revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and expensive process, often taking more than a decade. Quantum computers can significantly speed up this process by predicting the properties of complex molecules and their interactions with the human body more accurately than ever before. One interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung, allowing researchers to observe how drugs interact with human tissue in real time. Imagine a world in which we can model the human body in minute detail on quantum computers, creating digital twins that doctors can use to test treatments tailored to each patient. This approach could not only speed up the development of new drugs, but also improve their efficacy and safety many times over. It represents a shift towards more personalized medicine, where treatments are optimized for each patient's unique genetic characteristics. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across sectors. Its ability to solve complex logistical problems and optimize systems can lead to more efficient use of resources. For example, quantum algorithms have already improved cargo movement at the Port of Los Angeles, increasing throughput and reducing energy consumption. Space exploration can also benefit greatly from quantum computing. Navigating vast expanses of space requires processing vast amounts of data for trajectory alignment, system diagnostics, and life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation, and preserving critical satellite infrastructure. Research into black holes and quantum mechanics is not just a theoretical fad. It's shaping the very tools we expect to revolutionize our future. The insights gained from studying these cosmic mysteries are helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research into the uncharted reaches of the cosmos. So, quanta, in simple terms, are the smallest possible units of any physical property involved in an interaction, such as energy or matter, such as particles and photons. In classical physics, everything seems smooth and continuous. But at the quantum level, things like energy move in tiny, discrete packets, i.e. quanta, and that's why there are quite a few different methods of quantum computing, each exploring unique approaches to using these tiny units to generate enormous computing power. One of the leading techniques in current quantum computing research involves superconducting circuits. Companies such as Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures near absolute zero, allowing quantum states to persist long enough to perform complex computations. Another well-known method uses trapped ions and qubits. Companies such as IonQ and Quantinuum use this technique. where ions are held in space using electromagnetic fields and manipulated with lasers to perform quantum operations. This method boasts longer coherence times, meaning that quantum states remain stable for longer periods of time, although the speed of operation is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum with qubits encoded using photons, particles of light. This approach, promoted by companies such as Xanadu and startups affiliated with academic groups, operates at room temperature and uses the properties of light to perform quantum computing. Recent advances include Xanadu's development of a Borealis chip, which uses a novel method of manipulating groups of photons to gain quantum advantages. In turn, topological quantum computing, which has emerged from a more theoretical framework, offers a new approach to utilizing quasi-particles, particles that arise from interactions within a material. Microsoft's been a key player in this field, exploring ways to create and manipulate these quasi-particles to create qubits that are naturally immune to external perturbations, potentially solving the problem of quantum decoherence. In addition, one quite revolutionary approach to quantum computing is rapidly gaining momentum. This new method, using atoms held in optical tweezers, represents a significant leap forward in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative technology and learn how it has the potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are nothing new in physics, but their application in quantum computing is a new and rapidly developing frontier. By using lasers to capture individual atoms, scientists create qubits that are less susceptible to interference and easier to control than traditional methods. This technique is based on the unique properties of atoms. Being small and electrically neutral, they naturally avoid mutual interference that interferes with other types of quantum bits. This reduction in noise and interference is crucial to maintaining the coherence of quantum information, which is an ongoing challenge in quantum computing. A recent breakthrough in February this year involved the use of micro-lens arrays, which allow a significant increase in the number of atoms that can be manipulated simultaneously. These arrays allow thousands of atoms to be precisely arranged in regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange more than 1,000 atoms with remarkable precision. And these atoms are not just statically held, they are dynamically controlled, ready to perform complex quantum operations. The term supercharging accurately describes the improvement this method brings to quantum computing. By aligning two layers of micro-lens arrays and superimposing laser traps on them, scientists create a dense grid of atomic qubits. This arrangement not only increases the initial number of qubits, but also improves their overall stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows each qubit to be individually addressed and manipulated, opening the way to complex and large-scale quantum algorithms that were previously unattainable. When this new method's compared to existing technologies such as superconducting qubits and ion traps, the atoms in tweezers approach offers significant advantages in scalability and error reduction. Its ability to scale rapidly to thousands of qubits makes it a formidable competitor to better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation, but a very realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing complex problems, from cryptography to materials science, to be solved. As we conclude our journey through the quantum frontier, we find ourselves at a pivotal moment where quantum computing is moving from theoretical research to practical applications. The X Prize Quantum Applications Competition epitomizes this transition, presenting a challenge with a significant $5 million incentive to spur innovations that apply quantum computing to real-world problems. Over the next 3 years, teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, material science, energy, and other fields. This initiative not only accelerates the development of quantum technologies, but also emphasizes the potential of quantum computing to solve humanity's most urgent problems. By pushing the boundaries of quantum computer capabilities, X Prize aims to stimulate the transition from experimental quantum applications to everyday tools, making the fields of quantum mechanics accessible and useful to society at large. What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The infinite universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The post-inflationary multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, They share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmart's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the Many Worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the Many Worlds interpretation, at the moment of the coin flip, the universe is split into two. One where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe. And the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4. Ultimate Ensemble. The fourth level of Max Tegmart's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve, which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework, while levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results. Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. What if the relentless forward march of time, the ticking of seconds, the changing of seasons, the aging of our bodies, is nothing more than a grand illusion? What if the past, present, and future, the cornerstones of our existence, don't truly exist in the way we believe? For centuries, these questions have haunted philosophers, scientists, and everyday minds alike. Is time woven into the very fabric of reality, or is it a stubbornly persistent trick our brains play on us? The deeper we delve into the mysteries of the cosmos, the more a tantalizing possibility emerges. What if our entire reality is a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of objects themselves. Instead, they're creations of our brains as they interpret wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on an otherwise timeless universe. Consider the vibrant world of color that surrounds us. A juicy red apple, a field of yellow sunflowers, clear blue of a summer sky. At first glance, these colors might seem like fixed properties of the objects themselves. Yet the reality is far more complex. Colors don't exist independently in the world. They're born within our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of hues that shape our visual experience. This process isn't merely about biology. People with different forms of color blindness perceive the world in distinct ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling of time ceaselessly flowing forward, the division of our lives into past, present, and future, is merely a way to make sense of change within the universe. Maybe, like color, time emerges from the interaction between our consciousness and a reality that may be fundamentally timeless. The idea that time may be an illusion isn't new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the fabric of space-time, the question of time has persistently challenged our understanding. Today, we're going to delve into this enigma, exploring the scientific discoveries and philosophical riddles that hint at the possibility that time, as we experience it, may be nothing more than a grand cosmic deception. Time feels inescapable. It permeates our lives, from alarm clocks jolting us awake to the relentless countdown to birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute, unyielding force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton. He envisioned the universe as a vast stage with time serving as a universal clock, ticking away at the same steady rate for everyone and everything. But then came Albert Einstein, and our understanding of time was forever shattered. Einstein's theory of relativity revealed that time isn't a rigid constant, but a flexible participant in the cosmic dance. It bends, stretches, and warps depending on how fast you're moving and the strength of gravity's embrace. Imagine two identical clocks, one placed on Earth, the other aboard a spaceship hurtling near the speed of light. Bizarrely, if you could compare them, the clock on the spaceship would be ticking slower than the one on Earth. This mind-bending concept is time dilation. The faster you travel through space, the slower you travel through time. This isn't some abstract theory. It has real consequences. Imagine twins separated at birth. One stays on Earth, the other becomes an astronaut who spends years traveling at immense speeds. Upon their reunion, the spacefaring twin would have aged less than their Earth-bound sibling. Time would have literally passed slower for them due to the effects of time dilation. Time dilation may seem like science fiction, but it's a fact of our universe that engineers have to account for. GPS satellites, orbiting high above Earth and traveling at significant speeds, experience time slightly slower than we do on the ground. Their onboard clocks have to be adjusted to stay in sync, ensuring the maps on your phone remain accurate. Einstein's revolutionary theories upended our understanding of time. Suddenly, time wasn't a steady constant, but a dynamic player in the cosmic drama. This scientific upheaval sparked a resurgence in philosophical debates about the very nature of time. If time dilation and warped space-time are real, how do we reconcile these concepts with our everyday experience of time's constant flow? Let's explore some of the profound questions that emerge at the intersection of physics and philosophy. One central debate centers on the existence of the past and future. Presentists argue that only the present moment has any real existence. The past is a collection of memories, the future a realm of possibilities. Eternalists take the opposite stance, viewing all of the time, past, present, and future, as equally real and unchanging, like a vast unfurling tapestry. The growing block universe model attempts to bridge these two views. It posits a fixed past, an open future constantly branching into possibilities, and a continuously expanding present moment as our experience unfolds. These seemingly abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan for the future? If the future is already set, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and the choices we make within it. Perhaps the most unsettling implication of the block universe is the challenge it poses to free will. If the future already exists, laid out like a vast network of paths, are our choices truly our own? Or are we merely tracing a predetermined route? Our sense of agency nothing more than an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may already be written. Can the block universe coexist with genuine free will? Some philosophers argue that even if our actions are fixed within a timeless expanse, we still experience the act of choosing and the consequences of those choices. Others suggest that true freedom might lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to relentlessly march forward, never backward? Physicists and philosophers grapple with different arrows of time, each offering clues to the irreversible nature of events. The thermodynamic arrow is one of the most well-known. It stems from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This explains why eggs break but never unbreak, and why ice melts but doesn't spontaneously refreeze. These irreversible processes give us our sense of time moving in one direction. But thermodynamics isn't the whole story. Our minds create a powerful psychological arrow of time. We vividly remember the past, yet the future remains a mystery. Even the universe itself provides a cosmological arrow, as it continues to expand outward since the Big Bang. These diverse arrows raise a perplexing question. Is the flow of time a fundamental property of the universe, or a byproduct of how we experience the relentless unfolding of change? The bizarre realm of quantum mechanics throws a wrench into our traditional understanding of time and space. Consider the phenomena of entanglement, where two particles become linked in a profound way. Imagine a pair of gloves, one for your left hand, the other for your right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open one box and find a right-handed glove, you instantaneously know, faster than any signal could travel, that the other box contains the left-handed glove. In the quantum realm, particles can become similarly entangled, their properties inextricably linked. Measuring one instantly affects the other, even across vast distances, seemingly faster than the speed of light allows. This paradox hints at a universe where connections might exist outside our usual understanding of linear time. Theories like loop quantum gravity go even further, suggesting space-time itself isn't a smooth continuum, but made up of tiny, indivisible chunks like the threads of a cosmic tapestry. If true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of the way these fundamental building blocks interact. These mind-bending theories force us to question the very nature of reality. Could it be that our experience of time's relentless flow is an illusion, born from our limited perspective within a universe that may operate on principles beyond our current comprehension? Perhaps the past, present, and future we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the universe's greatest enigmas. Is it a fundamental force woven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion? A convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes hint at the possibility that our experience of time's flow may be profoundly different from the true reality of the cosmos. If time doesn't exist as we perceive it, what does that mean for free will and our place within the grand story of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws beyond our current grasp? We may never possess the definitive answers to these questions, but the very act of pondering them reveals the profound beauty and endless mystery of existence. While the relentless march of the clock and the turning of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continues continually defies our understanding. In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the Moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15-mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull. So-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument. which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide, combined with hydrogen from hydrothermal vents, to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JUICE mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, these missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JUICE and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. Have you ever heard of a galaxy that defies categorization? Imagine a cosmic structure that combines an ancient dormant core surrounded by a bright halo of young stars. This is not your typical spiral or elliptical galaxy, but something much more mysterious. A Hogue object. Initially mistaken for a planetary nebula or gravitational lens, the true nature of Hogue's object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue, teeming with new star formation. A clear gap separates the two components as if they belong to different galaxies. The object spans an impressive 121,000 light-years wide, with a central core about 17,000 light-years across and an outer ring stretching out 75,000 light-years. This apparent gap between the core and the ring is wider than the ring itself, which is a surprising feature for such a colossal galaxy. Ring galaxies, like Hogue's object, are extremely rare, making up less than 0.1% of all known galaxies. They often arise from complex cosmic events, but Hogue's object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision play a role? Arthur Hogue, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and puzzle scientists for decades to come. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, later named after him, had characteristics unlike any previously observed galaxy. At first glance, Hogue's object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, consisting of a central core surrounded by a luminous ring, suggested otherwise. Early images taken by the astronomer's telescope showed a clear separation between the inner and outer components, prompting curiosity and speculation. Initial hypotheses varied widely. Hogue himself hypothesized that it could be a planetary nebula, or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy at all, but rather a massive elliptical galaxy magnifying a background galaxy in a ring-like shape. Gravitational lenses occur when a massive object, such as an elliptical galaxy, bends the light of a more distant object behind it. This bending creates a ring of light around the foreground object, known as the Einstein ring. In early observations, the outer ring of Hogue's object resembled such a lens, suggesting that it may be a foreground galaxy amplifying the light of a more distant object. For nearly 4 decades, the true nature of the Hogue object remained uncertain. It was not until 1987 that astronomers equipped with better technology were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the red shift. This shift is due to the expansion of the universe, with more distant objects exhibiting a greater redshift. By analyzing the redshift of the core and ring of Hogue's object, astronomers confirmed that they're not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and cemented the status of the Hogue object as a unique type of galaxy. The central core, consisting of old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes Hogue's object from typical spiral and elliptical galaxies. Ring galaxies are rare, making up less than 0.1% of all known galaxies. Typical spiral galaxies have sprawling arms of stars, while elliptical galaxies have a more uniform, rounded shape. The Hogue object, with its perfectly separated nucleus and ring, remains one of the most well-defined examples of this rare class of galaxies. The discovery began the scientific journey to understand one of the most mysterious structures in the universe. Today, with the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its quiet appearance, distinct breakup, and combination of an ancient core with a young, star-forming ring make object Hogue a unique and enigmatic galaxy, prompting astronomers to investigate various theories of its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hogue object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. One a smaller galaxy collides with a larger galaxy, the impact generates a density wave that rushes outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring around the galaxy's nucleus. The Cartwheel galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hogue object, if a smaller galaxy collided with it, we would expect to detect several key features. First, the collision would create density waves that push the gas and stars outward, forming a ring. Moreover, the stars in the ring should have exhibited high relative velocities, indicating the kinetic energy from the collision. And third, in or near the ring, there would be residual fragments or remnants of colliding galaxies. However, detailed observations of Hogue's object have revealed some inconsistencies with the collision hypothesis. The ring stars do not exhibit the high relative velocities that are usually associated with such events. In addition, there's a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galaxy collisions have been used. These models show that although a collision may produce a ring structure, the resulting galaxy often retains traces of violent interaction. The Hogue object, which has a calm and symmetrical appearance, lacks these chaotic features, suggesting a more complex formation history. However, another intriguing possibility looms on the horizon: resonance theory. Could a galaxy's ring structure be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hogue object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of the internal dynamics of barred spiral galaxies, in particular due to resonance in the gravitational field. Spiral galaxies are characterized by the structure of a central bar, from the ends of which spiral arms branch off. These bars play a crucial role in the dynamics and evolution of the galaxy. According to theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions in which the rotational velocities of stars and gas clouds synchronize. These regions can trap gas and stars, resulting in the formation of rings. There are several basic types of resonances. Inner Lindblad resonance occurs near a galaxy center, often forming an inner ring. Outer Lindblad resonance arising further, potentially forming an outer ring. The third type is co-rotation resonance, a region where the rotational velocity of the bar coincides with the orbital velocity of the stars and gas, which can also lead to ring formation. In the case of the Hogue object, the presence of a ring around the elliptical core suggests that such resonances may have played a role in its formation. The bar structure could have caused a resonance that trapped gas and stars at certain radii, creating the distinct ring we see today. When the bar rotates, it exerts a gravitational influence that can reorganize the gas and stars of the galaxy. Over time, this process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism for how a spiral galaxy can evolve into a ring galaxy without a collision. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in ring formation. The central band and outer ring provide a visual analogy of what may have happened in Hogue's object. However, the resonance theory faces difficulties when applied to the Hogue object. In particular, the Hogue object currently has no central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory: the accretion theory. Can the gradual accumulation of intergalactic gas explain the unique structure of the galaxy? Let's explore this in more detail. The third major theory proposed to explain the formation of the Hogue object is the accretion theory. According to this theory, the unique structure of the galaxy resulted from the gradual accumulation of intergalactic gas, rather than from a dramatic collision or internal resonance. Accretion is the process by which a galaxy collects gas from the surrounding intergalactic medium over a long period of time. This gas is entrained by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hogue object, it's likely that a central elliptical core formed first. Over time, the gravity of this core attracted gas from the intergalactic medium. As the gas approached the nucleus, it began to rotate around it, forming a ring structure due to angular momentum conservation. As gas accumulated in the ring, its density reached a high enough density to trigger star formation. This process explains the bright blue color of the ring, indicating active, ongoing star formation. And the gap between the core and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies such as NGC 6028 provide an example of how accretion can lead to the formation of ring structures. These galaxies show similar features: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While the accretion theory provides a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How did the dynamics of gas influx and star formation balance create such a clear separation between the core and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence to support this theory. The ring of Hogue's object contains more gas mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic remnants are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory. By modeling the gravitational interaction in such ring systems, scientists have shown how the balance of forces can create stable and unstable orbits, leading to discontinuities in the distribution of matter. These results are consistent with the observed structure of the Hogue object, where the gap between the core and the ring is a region of unstable circular orbits, further supporting the theory. Also, the accretion theory offers a quite convincing explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has their own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object and the absence of residual fragments and high relative velocities commonly observed in such events. Resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring structures. However, it's clear that Hogue's object lacks the central bar necessary for this process, and the theory does not fully explain the apparent gap between the nucleus and the ring. Accretion theory, in turn, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius, and how the dynamics between the core and the ring create such a distinct gap. Despite these theories, several mysteries remain. Why is there a significant gap between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics within the galaxy interact to maintain this balance? Future telescope missions, such as the Nancy Grace Roman Space Telescope and the soon-to-be-launched Extremely Large Telescope, are designed to provide a deeper understanding of such questions. These advanced observatories will provide higher resolution images and more detailed spectroscopic data, potentially revealing the processes underlying the formation of such ring galaxies. As we explore the cosmos, Hogue's object remains a testament to the diverse and complex processes that form galaxies, and remind us once again that there are still mysteries in the cosmos waiting to be discovered. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Wennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. Amid the silent expanse of our solar system lurks a world of deep mystery and rugged beauty. Mars, with its purple dunes and ancient valleys, tells of its tantalizing past. It's a planet where sunsets color the sky blue, where towering dust devils run across the barren lands, and where the remnants of water streams silently tell the story of bygone days. Here, amid the red dust, lies the enigmatic brain terrain, a geologic marvel that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of Mars' most challenging mysteries. What forces created these enigmatic formations? Are they the key to unlocking the secrets of Mars' climatic past? As the sun dips below the horizon, the Martian sky transforms, casting blue light over the alien landscape. The scars of ancient rivers and cracks of dried mud tell a story of a time when water flowed freely on Mars, when the planet experienced the changing of seasons, and when this world may have been more Earth-like than we could have imagined. Yet for all of its wonders, Mars is a stark reminder of its alien nature. Today we'll travel to Mars, a world of beauty and mystery, a planet that holds the keys to our past and the promise of our future. Join us as we explore the mysteries of the good old red planet. Mars lies a canvas of geologic mysteries. Among them is the brain terrain. These complex patterns, reminiscent of the cerebral cortex, sprawl across the Martian mid-latitudes. Their origins are shrouded in mystery. What processes could have created such complex patterns? Scientists suggest that it's sublimation, the conversion of ice directly into vapor, that plays the key role here. Although the exact process remains cloaked in mystery, it's most likely the relentless interaction between the underground ice and the thin Martian atmosphere that forms the intricate patterns. But Mars is not a quiet world. It breathes and moves. Dust devils, those towering columns of cloying dust. rising kilometers into the rarefied atmosphere, are not just a spectacle of nature, but the architects of the Martian surface. They crisscross barren landscapes, leaving behind dark trails that testify to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 2 miles in height and are larger and more dramatic than their terrestrial counterparts. And then, as the Martian day fades, the sky transforms. A Martian sunset bathes the landscape in an ethereal blue light that contrasts sharply with the familiar red and orange hues of daytime. This phenomenon arises due to the unique interaction of sunlight with the atmosphere of the red planet, filled with dust of iron particles. As it passes through, the red part of the visible spectrum of sunlight is scattered by the dust particles, leaving only a mesmerizing blue glow. Although this scattered light colors the sky red, at sunset and night it transforms into shades of blue. But the mysteries of the Martian atmosphere don't end there. The interesting phenomenon of Mars' green glow, recently captured by NASA's Odyssey orbiter, provides a glimpse into the unique characteristics of the Martian atmosphere. This glow, observed from orbit, is the result of atmospheric processes that are common throughout the solar system, but manifest themselves differently on each planet due to variations in atmospheric composition and density. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms, which, when they hit the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors, but on Mars, the predominant color is green. This green glow is primarily due to the recombination of CO2 molecules in the upper atmosphere at an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions, where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to Earth's allows these luminous phenomena to be observed and studied more directly. It's also allowed the detection of other emissions, such as nitrogen oxide emissions in the ultraviolet spectrum, further enriching our understanding of the composition and behavior of the Martian atmosphere. Such atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable insights into the planet's past and present climatic conditions. Speaking of which, the Martian landscape, with its vast deserts and towering volcanoes, contains a wealth of clues about the planet's climatic past. Among them are signs of seasonal changes that have shaped the surface for millennia. The presence of features such as mud cracks, discovered by the Curiosity rover, which bear a striking resemblance to similar objects on Earth, suggests the presence of liquid water in the planet's past. In particular, the mud cracks are thought to have formed over many Martian seasons, indicating a cycle of wet and dry periods that Mars once experienced. Further evidence of Mars' dynamic climate can be found in the remains of ancient glaciers in the planet's mid-latitudes. These fossilized archives, imprinted into the Martian terrain, tell of a time when water ice slid across the planet's surface, carving furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, shape the terrain, leaving behind traces of their presence in the form of moraines and carved valleys. Such activity suggests that Mars has undergone significant climatic changes, perhaps similar to the glacial and interglacial periods seen on Earth. The presence of sulfate in the mud cracks adds another layer to our understanding of Mars' water history. Mud cracks, like those found on Earth, are formed by the drying of sedimentary rocks, indicating the presence of standing water that periodically evaporates. leaving behind these prominent patterns or subsiding beneath the surface. The detection of sulfates in these formations indicates that water interacted with the Martian soil, resulting in the deposition of minerals. The varying levels of these sulfates, combined with the pattern of mud cracks, paint a picture of a planet where water levels rose and fell, creating conditions conducive to chemical reactions that could even support the precursors of life. Clearly, it's the search for water on Mars that is a key aspect in understanding the planet's climate, geologic history, and potential for habitable life. Recent discoveries have shed light on the presence of water in various forms and locations on Mars, significantly changing our understanding of the red planet. On Mars, there are a great many geologic features that indicate the presence of water in the past. The discovery of ancient lake beds, river valleys, and outflow channels indicates that at one time, water flowed freely across the planet's surface. These features suggest that Mars once had a warmer and wetter climate, capable of supporting liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and river valleys further supports the idea of prolonged water activity that may have lasted thousands or even millions of years. One of the most revolutionary discoveries is the discovery of water ice near the equator of Mars. Traditionally, ice was thought to be found only in the polar regions of Mars, where it's visible on the surface. However, radar surveys and analysis have revealed subsurface deposits of ice at lower latitudes, including near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is much more widespread across the planet than previously thought. The implications of equatorial ice extend to the climate history of Mars and its potential habitability. Equatorial ice deposits indicate a more complex hydrologic cycle on Mars than previously thought. This could mean that in the past, Mars had a climate more similar to Earth's, with water cycling between the atmosphere and the surface. However, such a presence does not at all raise the possibility that conditions suitable for life existed on Mars in the past, much less in the present. Water is a key component of life, but such a contrasting climate change cannot offer much chance for a long process of development of any life forms. The search for biosignatures such as special minerals, organic molecules, or erosion patterns that may indicate past biological activity continues. Although no conclusive evidence of life on Mars has yet been found, the presence of water in various forms still retains a minimal possibility. Still, these water ice deposits could serve as a valuable resource for future human exploration and colonization of the planet, providing water for drinking, agriculture, and fuel production. Taking a closer look at the mineralogical landscape of Mars, we see that it's a stark contrast to the rich diversity found on Earth. About 6,000 different minerals have been discovered on our home planet, testifying to the dynamic geologic processes on Earth and the complex interaction between the biosphere and geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to the diversity of minerals through various biochemical interactions. By comparison, after 5 decades of research, only 161 minerals have been identified on the Martian surface. This divergence in mineral diversity is not just a numerical gap. It tells us a lot about the differences in the geological activity and history of the two planets. The scarcity of minerals on Mars has profound implications for our understanding and the planet's potential to support life. The diversity of minerals on a planetary body is often a reflection of its geologic and environmental dynamism. On Earth, plate tectonics, water availability, and atmospheric processes contribute to the wide range of physical and chemical conditions that are so essential for the origin and maintenance of life. Complex organic molecules, including the precursors to DNA, often require diverse chemical environments and catalysts. The limited mineral diversity on Mars, therefore, raises some questions about the habitability of the planet as a whole. The lack of diverse minerals on Mars also indicates that the planet may have had a more monotonous geologic history compared to Earth. However, is it as quiet and peaceful as it appears? Recent studies of the internal structure of Mars have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion, detecting what's believed to be the largest earthquake ever recorded on Mars. This earthquake, which lasted about 6 hours, did not fit the typical profile of a meteorite strike because no crater was left behind, suggesting it originated deep inside the planet. The magnitude of the quake, which was 4.7 on the Richter scale, hints at a significant geologic activity beneath the surface. Unlike Earth, Mars lacks plate tectonics, raising intriguing questions about the mechanisms causing these earthquakes. The lack of plate tectonics suggests that Martian earthquakes may be related to internal stresses or other geologic processes that we've not yet fully understood. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures beneath the surface, found by ground-penetrating radar from China's Churong rover, indicates a history of thermal contraction and expansion and speaks to the planet's former volcanic activity. These structures, ranging in size from a few inches to a few feet, have been found at depths of about 100 feet. Obviously, a dramatic change in climate or some cataclysmic event has caused these deposits to be so deep beneath the planet's surface. The region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further evidence of Mars' volcanic past. Located near the volcanic Tharsis Plateau, home to the solar system's largest volcano, Olympus Mons. This region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by ESA shows how the stretching and bending of the Martian crust in this region, resulting in the formation of deep valleys and canyons, is evidence of the planet's active geologic past. The release of water during organic eruptions may explain the presence of ancient river valleys and lakes, providing a glimpse into times when Mars may have been more Earth-like, with a warmer and wetter climate. Understanding the planet's volcanic history not only sheds light on its past climate and potential for life, but also helps in future research, as regions with past volcanic activity may hold clues to the planet's habitability and the availability of vital resources. Speaking of livability, it's impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement in space technology, successfully producing oxygen from Mars' carbon dioxide-laden atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in a variety of Martian conditions, both day and night, and in different weather states of the planet's atmosphere. Its ability to convert CO2 into oxygen through the process of solid oxide electrolysis is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen ions and carbon monoxide, and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity despite design trade-offs due to the mass, power, volume, and cost constraints associated with space missions. The success of MOXIE has profound implications for the future of human exploration and potential colonization of Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical life support resources. The study concludes that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for astronauts' life support, but also as a critical component of rocket fuel, Such a capability would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of the material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, taking a significant step toward realizing the dream of a self-sufficient human presence on the Red Planet. Speaking of the Perseverance rover, we should also mention its Ingenuity helicopter, which has far exceeded the original parameters of its mission on the Martian surface. Built just for a brief technology demonstration, Ingenuity was only supposed to make 3 flights within 30 days. However, it shattered those expectations by flying 72 missions over more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement was not only an important milestone in the aerial exploration of other planets, but also laid the groundwork for future missions. Ingenuity's journey was not without its challenges. It encountered and overcame numerous technical problems, including communication outages and unexpected landing scenarios. Despite these challenges, Ingenuity continued to push the limits of what was possible and even set a new range record on one of its flights. The vehicle's ability to survive and operate through Martian dust storms, extreme temperatures, and even sensor failure speaks to the reliability of its design and the team's careful planning. However, the mission ended in an unforeseen way when a significant part of the blade of one of Ingenuity's rotors was damaged, making further flight impossible. This incident marked the official end of Ingenuity's Mars mission. The helicopter's final flight took place in January 2024. However, the termination of Ingenuity's missions does not take away from its outstanding achievements and the invaluable data it provided. NASA has already begun applying lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon. The success of Ingenuity has opened the door to more ambitious use of aircraft for tasks such as sample retrieval, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it's worth noting that the endeavor to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the nadir of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling up to $11 billion. The complexity of safely extracting samples from the Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only unprecedented precision engineering and navigation solutions, but also significant financial outlays, which raises questions about budget allocation and priorities in space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate over international cooperation in Mars exploration is multifaceted, involving political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific return on missions through diverse expertise. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international constraints, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another, but not the last, test in our path is that as Mars becomes a center of exploration and potential colonization, the problem of space debris is becoming increasingly important. Debris accumulation in Martian orbit can pose a hazard to spacecraft, impede navigation, and jeopardize missions. This problem is not just theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris, and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. Mars colonization, once the stuff of science fiction, is increasingly entering the realm of possibility, thanks to technological advances and scientific discoveries. The successful demonstration of in situ resource utilization through experiments such as MOXIE, the potential to use local materials for construction, and advances in life support systems are gradually laying the groundwork for a sustainable human presence on Mars. However, the vision for colonization goes beyond technological challenges to include ethical, social, and environmental considerations. The responsibility of extending humanity's footprint to another planet raises questions about how we steward the Earth and the extent to which we will be able to apply these lessons to the New World. The future of Mars exploration is rich in promise and fraught with challenges. As we stand at the threshold of these endeavors, the collective wisdom, ingenuity, and cooperative spirit of the global community will play an important role in overcoming these challenges and realizing the dream of expanding humanity's presence beyond Earth. Imagine a time when the universe was a dark space, an era before the first stars lit up the heavens, a period known appropriately as the Dark Ages. It was a time when the cosmos lay shrouded in a cloak of mystery, filled with neutral hydrogen gas that hid the light, making the universe invisible to itself. But in this darkness, the seeds of change were sown. A pivotal event loomed on the horizon that would end the cosmic silence and usher in the epoch known as reionization. This transformative epoch remains one of the greatest mysteries since the Big Bang. The James Webb Space Telescope set out into the great unknown on a mission to unravel those very mysteries. Breaking through the veil of cosmic dawn, it offers us today a glimpse of an age when the universe awoke from darkness. What secrets are hidden in the light of the first galaxies? What forces ended the reign of the Dark Ages and heralded the beginning of reionization? And most importantly, how did these discoveries confirm or refute our theories of early expansion and the formation of cosmic structures? Join our journey to the very edge of space and time to trace the path of light back to its origins together. Just moments after the fiery birth of the universe in the Big Bang, the reality we know was unrecognizable. The newborn universe was a boiling cauldron of hot, dense plasma, a turbulent sea of subatomic particles colliding and combining in the extreme energies of the early cosmos. As the universe expanded, a cosmic interaction emerged in which matter and energy were linked by the rhythms of the nascent laws of physics. Expansion led to cooling, and within a few 100,000 years a transformation took place. Protons and electrons, once too energetic to bind, fused together to form the first neutral hydrogen atoms, casting a veil of darkness over the cosmos. This event marked the transition of the universe from a plasma state to a gas state, which led to the appearance of the cosmic microwave background, the first light of the universe, the faint afterglow of creation that can still be observed today. But along with this first light came the cosmic Dark Ages. Imagine a universe devoid of stars, where galaxies have not yet formed. A vast expanse of darkness pervaded only by the faint glow of the cosmic microwave background. Such was the universe during the Dark Ages, when light-emitting objects were absent and the all-pervasive neutral hydrogen gas formed a cosmic fog, absorbing any light that could ionize it. But in this darkness, the groundwork was laid for cosmic transformation. Dense clusters of gas began to gravitate toward each other, slowly thickening under the inexorable pull of gravity. These were the first steps toward forming the cosmic structures we see today, the precursors to the stars and galaxies that would eventually break through the darkness of the Dark Ages. As we plumb the depths of the origins of the universe, we are reminded of the profound transformations that shaped the cosmos. The Dark Ages, a period characterized by darkness and silence, were only a prelude to the events that followed. As the universe moved forward in time, leaving behind the Dark Ages, a monumental transformation was looming on the cosmic horizon. This was the age of reionization, a pivotal chapter in the grand narrative of our universe. Reionization refers to the process by which the neutral hydrogen gas that filled the early universe was ionized by the first light sources, effectively lifting the cosmic veil of darkness and allowing the universe to once again shine with light. This process is an important phenomenon in the history of our universe because it represents one of the few ways in which we can indirectly study the earliest stars and galaxies. Imagine the universe in a transitional period characterized by an abrupt transition from opacity to transparency. In it, the ubiquitous neutral hydrogen gas that once absorbed all ionizing light began to change. Tiny bubbles of ionized gas appeared as the first stars and galaxies formed, each becoming a cradle of light that pierced the surrounding darkness. These bubbles, at first few and isolated, began a journey of expansion and unification, marking the large-scale process of reionization that transformed the early universe. But what force was powerful enough to cause such a colossal change and gradually disperse this hydrogen fog? This question is at the heart of reionization, a mystery that astronomers and cosmologists have been piecing together clue by clue for decades. The prime suspects were the first luminous objects formed in the universe, the first stars and galaxies. These celestial formations, born from the gravitational collapse of dense regions in hydrogen gas, began to shine, their light making its way through the cosmic fog. According to the theory, the first stars were 30 to 300 times more massive than our Sun and millions of times brighter, burning for only a few million years before exploding as supernovae. Among these early stars, a special type known as population 3 stars, massive and incredibly bright, shone with a fierce light. Originally thought to be composed solely of hydrogen and helium, these stars were the first to break the cosmic silence. Their intense ultraviolet light was capable of splitting hydrogen atoms into electrons and protons. In other words, ionizing them. However, the history of reionization is characterized by complexity and nuance. As the bubbles of ionized gas grew and merged, the role of these early stars has come into question. Were they alone responsible for this cosmic transformation? Or did other, more numerous and less luminous objects contribute to the process? The mystery deepened with the realization that the reionization process was not uniform, but discontinuous, with the ionization regions expanding at different rates and different directions. This diversity suggested a variety of sources, each of which made a unique contribution to the overall picture. This was the time when the universe underwent one of its most dramatic transformations, a period that allowed light to travel unimpeded across the vast expanse of space. This very moment was captured by the afterglow of the Big Bang, the cosmic microwave background, or CMB. The CMB serves as a relic snapshot of the universe in its infancy, giving us a glimpse of conditions at the dawn of cosmic reionization. After reionization in the cosmos, a fundamental question arises. What forces were powerful enough to end the cosmic dark ages and ignite the universe with light. The search for these driving forces leads us into the heart of the unknown. So as we discussed earlier, among the prime suspects are the elusive stars of population 3. These theoretical giants, composed entirely of hydrogen and helium, are thought to be the first stars to crack the primordial darkness. Their intense ultraviolet radiation, capable of ionizing huge masses of hydrogen gas, makes them formidable candidates for reionization. However, their unstable nature and lack of direct observational evidence cast a shadow of mystery on their role. Another group of potential culprits are quasars, the extremely luminous nuclei of early galaxies, powered by supermassive black holes. These cosmic beacons, with their intense radiation, could ionize hydrogen gas over vast distances, carving out large ionized regions in the intergalactic medium. But like puzzle pieces that don't quite fit together, the distribution and number of quasars cast doubt on their ability to fully explain the observed ubiquitous reionization. However, the keen eye of the James Webb Telescope discovered that in the early universe, the cosmos is teeming with faint but unexpectedly numerous galaxies. These galaxies, less massive and less luminous than their later counterparts, may have played a more significant role in reionization than previously thought. Their abundance and the cumulative effect of ionizing photons emanating from them could have contributed significantly to the transformation of the cosmic landscape. If this were the case, instead of a few dominant sources, reionization could have been caused by a multitude of stars and galaxies, ending the Dark Ages. So what has JWST discovered? In the dense cosmic galaxy cluster Abell 2744, also known as the Pandora cluster, a whole bunch of unremarkable dwarf galaxies have been uncovered. The luminosity of such galaxies is more than 100 times fainter than our Milky Way. Gravitational lensing played a crucial role in this study, acting as a cosmic magnifying glass. It allowed astronomers to observe and study extremely faint galaxies from the early universe that would otherwise have been invisible even to the very powerful Webb telescope. By warping the very fabric of space, the massive Pandora cluster amplified the light from distant galaxies, making them appear larger and brighter. In their study, thanks to this magnification effect, astronomers took and analyzed the spectra of 8 extremely dim galaxies. Such modest celestial formations, often overlooked in the cosmic timeline, have come to the fore, changing our understanding of the evolution of the early universe. This particular type of dwarf galaxy holds a surprising secret for its modest size. It emits huge amounts of ionizing radiation, 4 times larger than previously thought. Astronomers estimate that 50,000 sources of near-infrared light are present in the Webb image of the galaxy cluster, Abell 2744. To arrive at this conclusion, the team first combined data from ultra-deep JWST images with additional Hubble Space Telescope images of Abell 2744 to select extremely dim candidate galaxies in the epoch of reionization. The near-spec near-infrared spectrograph was then used to study the emission characteristics from the distant objects. This discovery changes the paradigm of our perception of the initiators of cosmic reionization. For the first time, scientists have reliably measured the density of such faint galaxies and successfully confirmed that they are the most abundant population during the epoch of reionization. Their ubiquitous presence and significant ultraviolet emission indicate that they may have played a more important role in the end of the Dark Ages and the formation of the ionized landscape of the universe than previously thought. What makes dwarf galaxies particularly intriguing is their potential for uniform ionization. Unlike the large isolated bubbles created by more massive galaxies or quasars, the ionized regions around dwarf galaxies were likely smaller and more numerous, thus weaving together the complex network of light in the early universe. This complex structure of ionization with countless small bubbles thickening with time, paints a picture of reionization that's more gradual and widespread than previously thought. A similar, unusual family of dwarf galaxies was actually discovered back in the last century, in the mid-1920s, the so-called green pea galaxies. However, it took scientists a long time to explain what they are, having unambiguously determined only in 2023. These galaxies got their name for their compact size and green glow in optical images. Green peas are characterized by an amazing ultraviolet luminosity, indicating active star formation and the enormous amount of ionizing radiation they emit. These galaxies, although small in size, play a colossal role in the history of cosmic reionization. The James Webb Space Telescope has shed new light on these enigmatic galaxies, revealing their architectural legacy on the canvas of cosmic evolution. Along with galaxies such as Haro 11, known for their intense ultraviolet emission, the green pea serves as a living laboratory, allowing us to observe ionization mechanisms in action and further confirming the conclusions of a previous study. Not the least of these studies is the theory of cosmic inflation, a sharp and rapid expansion that's believed to have occurred a fraction of a second after the Big Bang. According to this theory, the universe underwent an exponential growth spurt that smoothed out all the initial irregularities and led to the homogeneous and isotropic universe observed in the cosmic microwave background. Looking into the epoch of reionization, JWST offers a unique vantage point to study these underlying theories. By observing the earliest galaxies and their distribution, we will be able to find echoes of inflationary fluctuations and assess their consistency with predictions. The distribution, size, and number of ionized regions created by the first galaxies and stars during reionization provide insight into the density fluctuations in the early universe that were amplified by inflation. Density fluctuations in the universe are like having a large room full of people with a little more people and a little more emptiness. Imagine the room is filled with people standing equidistant from each other. This is similar to the early universe, which was mostly homogeneous. However, in some parts of the room, groups of people may stand a little closer, creating crowding, while other places may be a little more empty. In the universe, these crowded and empty spaces are areas where there is a little more or a little less matter, stars, galaxies, and gas, than average. Over time, gravity pulls more matter into the crowded places, making them even more crowded, forming galaxies and galaxy clusters, and leaving the emptier areas even emptier as gaps between the crowded places. This is how the structure of the universe, with all its galaxies and vast empty spaces, emerged from these initial small differences in the distribution of matter. According to this model, such masses such as the first stars and dwarf galaxies formed first, which gradually merged to form the grand galactic structures we see today. Such nuances lead us to reflect on the complexities of the expansion of the early universe and to ask critical questions in the future research. How do these observations of the reionization epoch fit with predictions of cosmic inflation? Do they support a model of hierarchical structure formation? Or do they suggest refinements to our current understanding? A future web observing program called Glimpse will provide scientists with the deepest images of the sky in observational history, opening new windows into the earliest epochs of the universe. The study seeks to detect even fainter galaxies from the epoch of reionization. By targeting another galaxy cluster, Abel S1063, these observations will expand our cosmic census, potentially confirming the typicality of the dwarf galaxies observed in the current study and offering further insight into the large-scale distribution of galaxies in the early universe. This next step in the study could refine our understanding of the period known as Cosmic Dawn and the appearance of the first galaxies, shedding more light on the formation of the universe and its grand evolution.